I'm going to introduce electromagnetic fields. My lab purpose is visualizing the magnetic field of a paramagnet, understanding the distance dependence of magnetic field, and determining the magnetic dipole moment of the magnet. This is my overall lab result. I got distance dependence as -3, magnetic moment as 2.2817, and both are each experimental and computational magnetic field on 45 degree. These are my main physical principles. I use the Biot-Savart law to determine the magnetic field by magnitude, length, and direction. To determine the distance dependence value, I use the second formula, and I calculated m value in second formula using third one. Third formula is useful to make the linear graph by logarithmic change. To prepare this is my assumption. I'm now in the South Korea, so I have a for 50.186 micro Tesla, and my system is a phone with tabs, and surrounding is the mirror-sticks, magnet, and clear environment with other fields. And to prepare the experiment, I downloaded the magnetometer app on my phone, set the north direction for magnetic, and put the meter orthogonal mirror stick direct to the north, and made an intersection of the tape on my phone where location of the magnetometer chip. To determine on-axis field, I determined the distance field between the magnet and the magnetometer, which contributes a magnetic field 20 microtesla 3 times, and I repeated the step 1 and 2 with the different distances, which corresponding 70, 120, 170, and 220 microtesla. And to determine off-axis field, I determined the distance which has the 100 microtesla magnitude, then magnetic field, and recorded the Earth magnetic field Y component. And I added a perpendicular meter ruler and moved my phone up along added ruler by Y components. And finally, I calculate the vector magnetic field at the point. And for these sentences, I observed the first and the fourth sentences. I could observe the magnitude of magnetic field is gradually decreased by moving away from the magnet regardless of direction. Also gradually increased by moving closer to the magnet. This is my data for the on-axis one. You can see the logarithmic graph and equation of the distance by the distance. And this is off-axis data. In this data, I determined the experimental magnetic field vector on 45 degrees of axis here, and how far away from the magnetic distance. And using the equation from on-axis graph, I have a -3 as m value, this one, -3 value, and I get the L and K value as -40.6, and from these values I calculated a K, and with the N and K I calculate the magnetic field dipole as the 2.2817. This is my coding section. I put the magnetic dipole moment magnitude in red circle, this one, and I put the Biot-Savart law below and set the proposed scale and distance, and visualize the magnetic field on different axes, total 6 ones. And to visualize the 45-degree magnetic field, I put the distance and vector, and you can see the total 7 vectors for the magnetic field and computation of magnetic field vectors here. And you can identify the differences between experimental and computational magnetic field vectors. There can be errors like other distributing magnetic field around the experiment environment, incorrect direction setting, or wrong length measurement. However, you can see the quite similar two vectors. If I didn't direct north but laid out an intermediate angle with respect to Earth's magnetic field, then my result field will be varied by changed angle. And if I have two identical magnetic stub end by end to end, then my new magnetic field will be formed which has same direction and that doubled the magnitude of magnetic field. In conclusion, we proved that the magnitude of magnetic field is changed by distance, and each location of magnetic field has different direction, magnitude, and length.